In this video, I will show you how to sketch the graph of this function that involves fractional exponents using calculus. So here are the 5 steps that we always use to prepare to sketch a graph with calculus. Number 1, we need to find where the function is undefined. This will tell us vertical asymptotes. Step 2, we will use the first derivative test to find where the function is increasing and decreasing, and we will locate any extrema, relative max, relative min. Step 3, we will use the second derivative test to tell where the function is concave up or concave down, and we'll identify any inflection points. Step 4, we will find the limits at infinity. This will reveal the horizontal asymptote or slant asymptote if there is one, and it will tell us the end behavior. And step 5, it's always helpful to know the x and y intercepts. So let's get started. So step 1 is to identify any places where the function is undefined. This function doesn't have any undefined places. There are no fractions, no denominators to worry about. There's not even a square root. Notice the roots are the denominators. So we have a cube root. So there is no restriction on the domain at all. For that reason, we know that there will be no vertical asymptotes. Step 2 is to perform the first derivative test. So let's go ahead and find the first derivative. So we can simply use the power rule. So the 5/3 will come to the front and multiply times the 2, and that will give us 10/3 x. Then we must reduce this power by 1, so we're really subtracting 3/3, so that's going to give us 2/3. Same thing with the next term. We multiply the 4/3 times the 5, and that gives us 20/3 x. And reducing the exponent by 1, we are subtracting 3/3, so that will leave us with the 1/3 power. This is an expression for the first derivative, but I think it will be useful to factor out a common factor. So let's go ahead and do that, which can be a little bit tricky sometimes, especially with fractions and such. So as far as the constant in the front, I think the greatest common factor is going to be 10/3. So we're going to pull that out to the front. Now when it comes to the variables, you always want to go with the lower exponent. So 1/3 is the lesser exponent. So I'm going to pull out x to the 1/3 power. So now I need to carefully decide what will go inside. So obviously we pulled out the 10/3, so the first term will have no coefficient. The easiest way to deal with the variables is to just subtract the exponent that you're pulling out. So since I'm taking out x to the 1/3 power, to figure out what's going to be happening with the x, I can just subtract 1/3 from this power. So that's going to leave me with x to the 1/3 power. Okay, now 20/3 divided by 10/3 is 2. And we're taking out the entire x to the 1/3 power, so there won't be any variable here. Or you could look at it as subtracting 1/3, and that would make the 0 power. X to the 0 power is just 1, which you don't have to write down. Either way you want to look at it. Okay, so that's it. We have this nice expression for the first derivative. So for the first derivative test, we need to find the critical numbers. And the critical numbers occur when the first derivative is equal to 0, or when the first derivative is undefined. Okay, so let's see where the first derivative is equal to 0 by simply setting this expression equal to 0. So that will give us 10 thirds, x to the 1/3 power times x to the 1/3 power minus 2 is equal to 0. Using the zero product property, I'm going to set each of these factors equal to 0. So I will have 10 thirds x to the 1/3 power equals 0. And I will have x to the 1/3 power minus 2 equals 0. So if I divide both sides by 10 thirds, I have x to the 1/3 power is equal to 0. And if I cube both sides, I will have x equals 0. So this is my first critical number. Now, so I almost skipped over to the undefined, but I was forgetting about my x to the 1/3 power minus 2 equals 0. Adding 2 to both sides, I get x to the 1/3 power is equal to 2. To get the x by itself, I'm going to cube both sides. That cancels out this exponent, and so that will leave me with x equals 8. So I have two critical numbers. Now, as far as the undefined, there are no places where the function, where the first derivative is undefined. There are no denominators or anything like that to worry about whether or not they equal 0. So there will be no critical numbers here. So now we need to take these critical numbers and use them to divide the number line into intervals for the first derivative test. Okay, I'm going to use white numbers to show the critical numbers, and I'll use colored numbers for my test values. So let's see, I'll put 0 about here. Okay, and it's a critical number, so I'm going to mark it in white, and I'll put 8 over here. And that's a critical number, so I will mark it in white. So I will do my test numbers in color. So I'm going to need a test value over here, so I might as well pick -1. And I'll need another test value in the middle interval, and I'm just going to pick a +1. This is not going to be to scale, by the way. And we'll need another test value over here. So you know what? I'm going to be very clever about how I pick this number. Usually we just pick numbers as small as we can. So maybe I would just pick 9. But I'm not going to do that because I'm noticing that I have x to the 1/3 power. That's the cube root. So it will be advantageous if I pick a number that has an even cube root. Okay, so for example, 27. So even though that's a much bigger number, I know that the cube root of 27 is 3. So this will be a good one to use. All right, so let's go ahead and evaluate each one of these test values using the first derivative. So I'm going to actually mark this side of the line with an F prime to show that my calculations are first derivative evaluations. Okay, so I'm starting off with this -1. So I'm going to have 10 thirds. Maybe I can squeeze this on camera here. So I'm going to have 10 thirds times -1 to the 1/3 power. And then I will have -1 to the 1/3 power minus 2. Okay. So all I care about is whether or not this is positive or negative. So -1 to the 1/3 power is just going to be -1. So out here in the front is going to be negative. So I'm just going to keep track of that. Now inside of the parentheses here, negative 1 to the 1/3 power is negative 1. So I have negative 1 minus 2, that's negative 3. All I really care about is this is negative. But a negative times a negative is a positive. So the first derivative test tells us whether or not the function is increasing or decreasing. So this positive tells me that the function is increasing in this interval. So I will show that with this little increasing arrow. So let's move on to positive 1. Okay, so maybe I can squeeze it in below this a little bit. So I'm going to have 10/3 times positive 1 to the 1/3 power. And then positive 1 to the 1/3 power minus 2. Okay, so out in front, everything is positive. So I'm going to have a positive out there. And then inside the parentheses, 1 to the 1/3 power is 1. 1 minus 2 is negative 1. So I have a negative inside there. A positive times a negative, of course, is a negative. So this negative value tells us that the function is going to be decreasing in this interval. And finally, the 27. So I'm going to have 10/3 times 27 to the 1/3 power. Okay, and 27 to the 1/3 power minus 2. Okay, well, out in the front, this is all positive. So I'm definitely going to have a positive going on out there. And then inside of the parentheses, 27 to the 1/3 power is 3. And because it's just the cube root of 27. And 3 minus 2 is 1, positive 1. So I'm getting an overall positive value in this interval, which tells me that the function is increasing during this interval. Notice that the function went from increasing to decreasing right here at 0. That tells us that we have a relative max happening right here. So we have a relative max at 0 comma something. Let's find the y value that goes with it. Okay, so if we evaluate the function at 0, well, we can just do this mentally real quick, because if you substitute 0 in here and here, you're just going to get 0. So we have a relative max at the point 0 comma 0. Meanwhile, over here at 8, the function goes from decreasing to increasing, which means that we have a relative min here, since neither one of these are asymptotes or anything, so this will be a relative min. So let's substitute 8 in and get the y value that goes with this. So let's do f at 8 would be 2 times 8 to the 5/3 power minus 5 times 8 to the 4/3 power. So guys, remember that a fractional power is in the form power over root. So this is the cube root and the 5th power. So I'm going to go ahead and do the cube root first. So the cube root of 8 is 2. So this will become a 2. So I still have the 5th power left behind. And again, the cube root of 8 is 2, and I'll have the 4th power left behind. Now 2 to the 5th power is 32. and 2 to the 4th power is 16. So this is going to be 64 minus 80, which is negative 16. Which means that we have a relative min at 8 comma negative 16. So now it's time for the second derivative test. So we're going to use the power rule. 2/3 times 10/3 is going to be 20/9. And then we must, of course, reduce this by 1. So we're subtracting 3/3, which will be negative 1/3. Now, 1/3 times 20/3 is going to be 20/9. And then again, we must reduce this by 1. So we're subtracting 3/3. So this will be negative 2/3. Again, it will be useful to rewrite this in factored form. So let's go ahead and factor this. Conveniently, I see we have this 20/9, so that will definitely be part of our GCF. With the variable part, you want to take out the smaller exponent. So don't forget, these are negative. So negative 2/3 is actually less than negative 1/3. So I need to take out x to the negative 2/3 power. So the way we understand what goes inside the parentheses, the easiest thing to do with the exponents is to subtract the exponent that you're taking out. So in other words, I need to subtract negative 2/3. But we all know that when you subtract a negative, you end up adding. So I'm going to really have x to the 1/3 power. All right, negative 1/3 plus 2/3. That's positive 1/3 power. Now for the other term, notice that the GCF is the entire thing. So this is just going to be a 1. Because the x to the negative 2/3 power has a negative exponent, this has to drop down to the denominator. So let's go ahead and rewrite this entire thing as a big old fraction. So I'm going to have f double prime of x is equal to, let's get this fraction going. So let's start with the 20/9. So obviously 20 is in the numerator and 9 is in the denominator. As I mentioned, x to the negative 2/3 power has to drop down. So I'm going to have x to the 2/3 power in the denominator. The parentheses x to the 1/3 power minus 1 will stay up here in the numerator. Now it's time to find the possible inflection points, similar to the critical numbers of the first derivative test, and these will occur where the second derivative is equal to 0 and where the second derivative is undefined. So where will the second derivative be equal to 0? When you have a fraction, if you want a fraction to equal 0, the only way for that to happen is if the numerator equals 0. So this boils down to having just the numerator equal to 0. So dividing 20 on both sides, we have x to the 1/3 power minus 1 equals 0. Adding 1 to both sides, we have x to the 1/3 power is equal to 1. Cubing both sides, we have x equals 1. So this is our first possible inflection point. So where is the function undefined? The second derivative will be undefined where the denominator is equal to 0. So that would be 9 x to the 2/3 power equals 0. Dividing by 9 on both sides, we have x to the 2/3 power equals 0. And raising both sides to the 3/2 power, we end up with x equals 0. So we have two possible points of inflection, which we will use on the number line to find the intervals to test. So here we are back at the number line. I'm going to label this side of the number line with f double prime to remind us that the calculations that we do here will be evaluations of the second derivative. The two possible points of inflection were 0 and 1. So I'm going to mark them in white on this side of the line. So I'm going to put a 0 here, and I guess I'll put the 1 here. So now these are the numbers that we will use to find the intervals. So I'm going to have to pick test values in each of these three intervals for the second derivative test. In the first interval, I think I will use -1 again. In the second interval, I'm going to squeeze in here a 1/2. Okay, so I'm going to use a test value of 1/2. And in the third interval, I think I'm going to use 8. And I'm putting these three numbers in color to show that they are test values, not potential points of inflection. So let's go ahead and evaluate at -1. So we're going to have 20 times -1 to the 1/3 power minus 1. And that's going to be over 9 times -1 to the 2/3 power. So remember that a fractional exponent is in the form power over root. So sure, this is the cube root of -1, but then after that we're going to square it. So because of the squaring, this is definitely going to be positive. So the denominator here is going to always be positive no matter what we put in here. So we can just focus our attention on the numerator. So in the numerator, we have the cube root of -1, which is still -1, minus 1 is -2. So we have 20 times -2. So the numerator will be a negative value. And of course, a positive divided by a negative is a negative. So the overall value of the expression is negative. This tells us that the function will be concave down in this interval. You know what, guys? I just changed my mind on using the 1/2 as a test value. I'm remembering that I'm going to have to do the cube root. So it would be smarter to pick a number that I can easily take the cube root of. So instead of 1/2, I'm going to use 1/8, which is still in this same interval. So that's going to give me 20 times 1/8 to the 1/3 power minus 1. Nine times 1/8 to the 2/3 power. So remember, we already know the denominator will be positive because of the squaring. So I don't even need to analyze this any further. In the numerator, 1/8 to the 1/3 power, that's the cube root of 1/8, is 1/2. So I have 1/2 minus 1, that's going to be a negative number, times 20 will be a negative number. So in this interval, we again will have a negative value. So this is a second interval where the function is concave down. Moving on to the final interval and a test value of 8. So we will have 20 times 8 to the 1/3 power minus 1 over 9 times 8 to the 2/3 power. So we know the denominator is positive. The cube root of 8 is 2. 2 minus 1 is positive, times 20, still positive. So the overall value is positive, which tells us that the function will be concave up in this interval. Notice that the function goes from concave down to concave up at 1. That means we have a point of inflection at 1 comma something. Let's go ahead and find the y value by evaluating the original function at 1. So this would just be 2 times 1 to the 5/3 power minus 5 times 1 to the 4/3 power. But of course, 1 to the 5/3 power is still just going to be 1. And to the 4/3 power is still going to be 1. So really it's just 2 minus 5, which is negative 3. So we have a point of inflection at 1 comma negative 3. Next, it is time to look at the limits at positive infinity and negative infinity to determine the end behavior. When you have a string of terms like this, the only term that matters is the highest degree term, the one with the largest exponent. So we can just look at this term and we can really forget about the other term for these purposes. As x approaches positive infinity, this term will just get bigger and bigger and bigger, and it will always be positive. We're talking positive infinity, so x is a larger and larger positive number. So the function will increase without bound. As x approaches negative infinity, so now we're talking about negative x values, but because the numerator and denominator are both odd values, these negative numbers will stay negative. So as x approaches negative infinity, the value of the function will just get more and more and more negative. So in other words, the function will decrease without bound. This means that there are no horizontal asymptotes, but this does tell us the end behavior. On the right, it rises, and on the left, it falls. The final information we need to gather is the x-intercept and the y-intercept. The y-intercept is super easy. Let's just knock that out. For the y-intercept, we will just evaluate the function at 0, which we can do mentally. If we substitute 0 in for both of these x's, we're going to get 0. So the y-intercept is simply going to be 0, 0. For the x-intercept, we need to set the function equal to 0. So that's going to be a little bit more challenging. So we're going to have our 2x to the 5/3 power minus 5x to the 4/3 power equal to 0. In order to solve this, we should factor it like we've done with the first derivative and the second derivative. So looking at the constants, there's nothing common. So I'm just going to deal with the variable. remember, for the variable, you take out the power of x that is the smallest. So obviously 4/3 power is the smallest, so we will take out x to the 4/3 power. And remember, to figure out what goes inside with the variable, you're going to wind up subtracting the power of x that you took out. So we're going to subtract 4/3. Okay, and technically we're doing the same here, but it'll be gone. So we will have x to the 1/3 power minus 5. Okay, we took out the entire x to the 4/3 power, so it's just out here, it's gone. All right, now we can use the zero product property and set each one of these factors equal to 0. So x to the 4/3 power equals 0, and 2x to the 1/3 power minus 5 equals 0. If I raise both sides to the 3/4 power, I get x equals 0. So one x-intercept is now found. It would be 0, 0, which we kind of already knew because the y-intercept is 0, 0, and that's on the x-axis as well as the y-axis. But what about this other equation? Adding 5 to both sides, we have 2x to the 1/3 power is equal to 5. Dividing both sides by 2, we get x to the 1/3 power is equal to 5/2. Cubing both sides of the equation, we will get x is equal to 125 over 8. So this gives us another x-intercept of 125/8, 0. Which, by the way, is approximately, it's going to be 15.6. All right, just for graphing reasons. Let's start by graphing the key points. So we have a relative max at 0, 0, a relative min at 8, -16, a point of inflection at 1, -3, as well as an x-intercept at 125/8, 0. So here are those 4 key points that we found. Now let's look back at our chart and see where the function should be increasing and decreasing and concave up and concave down. From -infinity to 0, the function should be increasing while concave down. That would look something like this. From 0 to 1, the function should be decreasing while concave down. This will be a little bit tough to draw. That should look a little like this, decreasing while concave down. For the rest of the graph, the function is decreasing down to the relative min and then increasing. And of course, it was concave up the whole time that it did that last stretch. So this is our final answer. This is our graph of the function. Let's compare it to the actual graph off of Desmos. Kabam! Nailed it.